Welcome to This Explainer. Today, we're diving straight into exam mastery for Cambridge IGCSE Computer Science, and we are tackling the really fascinating world of data transmission. Have you ever actually stopped to think about how a photo you send from your phone just magically appears on a friend's device halfway across the world in literal milliseconds? Well, spoiler alert, it's not magic. It is an incredibly precise, highly orchestrated system. In this explainer, we're going to break down the exact journey of data from sender to receiver. We'll decode how it travels, how we spot mistakes along the way, and crucially, how we keep it safe from prying eyes. To help you mentally organize all these complex networking concepts for your exam, here's our roadmap. First up, we're looking at the data packet journey. Second, methods of transmission. Third, catching transmission errors. And finally, securing data with encryption. Let's get right into it. Starting with Section 1, the data packet journey. Okay, so the very first major problem of networking is basically logistics. We've got massive files, right? High-definition videos, huge documents, and we need to move this information across a global network. We can't just shove a massive file down a cable all at once. It just doesn't work. So how do we do it? The solution is actually surprisingly simple. We chop it up. We break that large data down into small, really manageable chunks, and we call these chunks packets. But here's the catch. Once you have literally thousands of packets floating around the internet, how on earth do they know where to go? That's where the Internet Protocol, or IP address, comes in. Think of an IP address like a digital home address. It's a unique string of numbers that identifies exactly which computer on the network is sending the packet and which one is supposed to receive it. Now, what's really interesting is how a packet is actually put together. It isn't just raw data. It's broken into three critical components. First, you've got the packet header. This contains the IP address of the originator, the IP of the receiver, and a specific packet number. That packet number is absolutely vital because packets don't always take the same route. That's a process called packet switching. So they might actually arrive totally out of order, and the receiving computer relies on these numbers to rebuild the file properly. Second is the payload. This is the good stuff, the actual bundle of data you're trying to send. And third, the trailer, which is sometimes called a footer. This basically taps the receiving device on the shoulder and says, hey, this is the end of the packet, and it includes a built-in validation check just to make sure the data wasn't completely scrambled in transit. Moving right along to Section 2, methods of transmission. So our data is neatly packed and ready to go. Now let's explore the different digital highways these packets can actually use to travel. This is all about direction and speed, and you'll definitely want to memorize this breakdown for your exam. We have three main types of transmission. Simplex is one way only. Think of a keyboard sending data to a monitor. The monitor doesn't type back. Half duplex is two-way communication, but not at the same time. And full duplex is two-way simultaneous communication. This is exactly like a standard telephone network where both people can talk and listen at the exact same moment. To really nail down that half duplex concept, think of a set of walkie-talkies. They illustrate it perfectly. When you hold down the button to speak, you're using the full bandwidth of that channel. That's great for clear audio. But your friend on the other end literally has to wait until you let go of the button before they can reply. So data can flow in both directions, just never simultaneously. Beyond just the direction, we also need to consider how the actual bits are grouped as they travel. And here we contrast serial and parallel transmission. Serial transmission sends one bit at a time, sequentially, down a single wire. It's a bit slower, sure, but it is incredibly reliable and very cost-effective over long distances because there's almost zero chance of the bits getting jumbled up. Parallel transmission, on the flip side, fires multiple bits simultaneously down multiple channels within the exact same cable. It's way faster, but it's more expensive and much more prone to synchronization errors. Basically, bits can arrive slightly out of sync if the cable is too long. All right, on to Section 3. Catching transmission errors. Let's transition to the second major problem in networking. Look, just moving the data isn't enough. We live in a messy world full of electrical interference, faulty cables, and random system glitches. Data corruption is gonna happen, so we need really robust tools to catch broken data the moment it arrives. The absolute simplest defense mechanism we use is called a parity check. Here's how it works in 3 quick steps. First, the sending and receiving computers agree on a protocol. Are we going to use even parity or odd parity? Second, the sender looks at a 7-bit byte of data, counts up the number of ones, and adds a final 8th bit, the parity bit, to make the total number of ones match that agreed-upon protocol. So, for example, if they agreed on even parity and the 7-bit byte has 3 ones, the parity bit becomes a 1, making the total 4, an even number. Finally, the receiver verifies the total number of ones upon arrival. If it counts an odd number when it's expecting even, boom, the computer instantly knows the data is corrupted and asks for it to be sent again. But as you might guess, parity checks aren't completely foolproof. So we have alternative error checks. Checksum is a bit more advanced. It runs a complex mathematical algorithm on the data block right before it leaves, generating a specific value. The receiver then runs the exact same algorithm. If the answers match, the data is good to go. Contrast that with the incredibly simple echo check. This one is exactly what it sounds like. The receiver just bounces a complete copy of the data straight back to the sender and basically says, hey, here's what I got. Does it match what you sent? It's super simple, but obviously it eats up a lot more bandwidth.
So the big question is, what actually happens when an error is found, or if data just goes completely missing? Enter RQ, or automatic repeat requests. You can think of this as the persistence engine of data transmission. It relies entirely on acknowledgements. If a receiver gets good data, it sends a positive acknowledgement. If the data is bad, it sends a negative one. But what if the data is just totally lost in transit and never arrives? Well, RQ uses something called a timeout. If the sender doesn't hear back within a specific time frame, it just assumes the packet dropped and automatically resends it. And it will keep doing this over and over until it gets that positive confirmation.
Now, we've talked a lot about computer-generated errors during transmission, but what about human error? What if a cashier misscans a barcode at the store? Take a look at this number 5. In a real toy store barcode we analyzed for this explainer, this specific digit sits at the very end of the sequence. It's known as a check digit. This check digit is essentially a brilliant mathematical trap designed to catch human error. When a barcode is scanned, the computer isn't just mindlessly reading the numbers, it performs a rapid-fire calculation using all the preceding digits to ensure they were actually read correctly. For example, it might follow an algorithm that looks like this. Add digit 1 to digit 8, divide the result by digit 2, and then add digit 10. The result of that exact arithmetic must equal our check digit, the number 5. If it churns out a 4 instead, the computer instantly knows the scanner missed a line or a human typed it in wrong, and it rejects the input. It's a fully automated, built-in quality control check. Finally, let's look at Section 4, Securing Data with Encryption. All right, we are entering our final challenge. Think about it. The data was chopped into packets, it traveled down the right transmission highway, and we checked it for errors. It arrived totally intact. Awesome. But what if a hacker intercepted our packet while it was traveling across the public internet? This is where encryption steps in to save the day. And interestingly, as our source material points out, the origins of encryption can actually be traced all the way back to Julius Caesar in Roman times. He used the Caesar cipher, physically shifting the letters of the alphabet forward or backward to turn a readable message, which we call plain text, into unreadable ciphertext. We do the exact same thing today, just with unimaginably complex mathematical keys instead of simple alphabet shifts. Let's break down the two modern methods for doing this. Symmetric encryption is the simpler method. It uses one single secret key to both scramble and unscramble the data. But there's a massive flaw here. You have to share that secret key with the receiver. And if the hacker intercepts the key while you're sharing it, well, game over. They can read everything. That is exactly why asymmetric encryption is the absolute gold standard for secure internet transactions. It uses a pair of keys. You give literally everyone your public key, which they can use to encrypt a message and send it to you. But crucially, that public key cannot reverse the process. The only thing on Earth that can decipher the message is your closely guarded private key, which you never ever share with anyone. It is just a brilliant system. Let's bring all of this together. The mind map we're pulling from our source material perfectly visualizes the entire ecosystem we've just explored. You can see the data packets right at the start, branching out into our transmission methods: serial, parallel, simplex, duplex. Then you see the error checking mechanisms acting as a crucial safety net. And finally, the encryption protocols locking all that data down. Every single time you load a web page or send a message to a friend, this entire magnificent process happens in the literal blink of an eye. So, as we wrap up this explainer, I really want to leave you with a question to think about as you prepare for your exams. Which of these data transmission concepts is your biggest hurdle right now? And how will you apply the structures we discussed today to overcome it? Whether it's memorizing the difference between half and full duplex, or wrapping your head around the logic of asymmetric encryption, just break the concepts down exactly like a data packet. Thanks so much for joining me today, and keep learning.